All right, then the topic of the moment is larger organic molecules and how we might throw one of them at you on an evaluation, seeing if you can think about lone pairs, hybridizations, bond angles, sigma and pi bonds, etc., etc., etc. So hopefully in this point you're toward the end of your studies in Unit 4 on bonding. Almost think about geometries of molecules and such. So here's an interesting vitamin, vitamin B6 phosphate. I see a phosphate group over here with a phosphorus and some oxygen surrounding. But vitamins and organic molecules, biomolecules, often very, very big and large. This one looks like it has a ring of 6 carbons, no, a 6 membered ring with a nitrogen there. Carbon likes to make 4 bonds, 1, 2, 3, 4, 1, 2, 3, 4. Count them all the way around. Carbon almost always makes 4 bonds. Looks like this alternates double, single, double, single, double, single around like that. We might be told this is a positive charge. Usually we are told the nitrogen has a positive charge if it has an extra H plus on it per se. If I took that H plus off, it will have a lone pair there. And speaking of lone pairs, organic chemists often get lazy and don't bother to draw the lone pairs. So let's do that. And we know oxygen loves to have 2 lone pairs. Nitrogen likes to have a lone pair as well, unless it has 4 bonds, 1, 2, 3, 4. Phosphorus might even have lone pairs, but it's gone crazy in its expansion of its octet. Or it also helps sometimes to think about, oh, here I see I've taken off that hydrogen. What if I took off that hydrogen right there? By that I mean a strong base or a basic type thing. A Lewis base looks for the H plus, rips off the H plus and leaves behind the nitrogen with its lone pair. So that's a possibility. Or I could draw like this, like a lone pair is a blob of, it's usually in these cases an unused p orbital with 2 electrons hanging out. Well, if I did that for the lone pair of nitrogen, couldn't I also do that for the lone pairs on oxygens? Certainly could. Looks a little bit messy, and it's rarely ever done that way, but it's good to think about that those negatives are there acting as potential Lewis bases looking for H pluses to attract. Looks like it went back. Oh, what did I do here? I could, if I had a strong base, I could also remove one of these hydrogens here. This is a hydrogen attached to an oxygen with several other electronegative regions around it. So this hydrogen or this hydrogen, they're both equal, could probably be yoinked off and create an even, I shoulda, coulda, woulda. Interesting. Maybe I should have labeled this an ion right here. If I lost that H plus, there would be a negative charge that would dwell amongst these over here. Well, in any case, have you studied hybridization? There's a really simple way. If you haven't, by the way, you should go back and rewatch this video, or maybe watch it once now and go back and watch it again later. Hybridization on a central atom questions how many regions of electron density are around or about that atom, including bonding pairs and lone pairs. Although curiously, a double bond doesn't count for extra in determining hybridization. So if I have 2 regions of electron density around an atom, that's just called sp hybridization. 3 regions of electron density, maybe 2 bonding pairs and a lone pair, or maybe 3 bonding pairs. I didn't say that right. Anyways, it's not. I didn't make a mistake, but I should have put it. Let's go on with another example. 3 regions of electron density, sp2. Most commonly, 4 regions of electron density, sp3, which would mean the octet, or an expansion of the octet in 5 and 6 regions of electron density. Doesn't happen very often. But looking at this one, I think I color-coded this little bad boy here. Oh yeah, I did. So if I dare to count, 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1. Oh my goodness. Oh yeah, right. 1, 2, 3, 4. Doesn't count extra. 1, 2, 3, 4. 1, 2, 3, 4. So the blue ones look like they have the sp3 hybridization. The brown ones, as I've coded them, look like they have 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3 regions of electron density. So did you notice I'm not counting the double bond as an extra region, but I am counting the lone pairs as a region in and of themselves as regions of electron density. Oh yeah, and by the way, the bond angles. The bond angles may seem confusing, but if you've studied anything in chapter 5 with regards to geometries, it boils down to something really simple. If they're just if it's just two atoms bonded together, or maybe three in alignment, that's 180 degrees. Or three atoms in a, do I have any of those on the trigonal planar? Oh, I do. Like right here. These carbons right here. These carbons in the ring have 1, 2, 3, 1, 2, 3, 1, 2, 3 regions of electron density, so that would be 120 degrees from here to here, here to here, here to here, etc. And the same all the way around. Even this nitrogen with its lone pair and two bonding pairs would have a 120 degree angle. But if I look at just this carbon, hydrogen, 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 this could also be a hydrogen if you wanted it to be simple and called a methane molecule. But I know that 4 regions of electron density spread evenly throughout space has an angle of 109 degrees. Did you remember that? Same story for this oxygen up here with 2 lone pairs and a bonding pair and a bonding pair. This would be about 109, although we know in water like H2O, if this were another H, those lone pairs push those bonding pairs of hydrogen a little bit closer than 109, but yeah, who cares? Just remember 109. Yeah, interesting. So you have to break it down bit by bit, part by part. So if I were looking, say, at this oxygen right here, I just look at 1, 2, 3, 4. That's sort of tetrahedral in nature, and therefore it's sp3 hybridization, and the bond angle is 109. On the other hand, if I look at this oxygen up here, I think about lone pair, bonding pair. That's trigonal planar. I suppose it's trigonal planar between this bond and these lone pairs. Although since this oxygen isn't bonded to any of their atoms, we would kind of rarely ask for the geometry of electron density around that oxygen, but you could. Think about it. It's just a blow-up version, I guess, of that portion of the phosphate. Oh, there, I did it right there, didn't I? I showed the sp3 hybridization on that oxygen, sp2 hybridization on this oxygen. This would be sp3 hybridization, and this would be sp3 hybridization. This one's diminished because of that that double bond there. We could then throw different weird molecules at you and say pick it apart. Look at the different components. I don't actually think I have these answered, and so I'll leave them to you to struggle with or enjoy. But here's another phosphate group. Atom 1, oxygen, atom 2, this carbon, atom 3, this nitrogen, atom 4, atom 5. And by the way, when you're presented with a complicated looking multiple choice question like this, don't even look at the answers. Just go through and try to say, what's the hybridization on this? Write it down. What's the hybridization on this? Write it down. By the way, this is sp2, this is sp3. What's the hybridization on this? 1, 2, 3. Looks like sp2. What's the hybridization on this? 1, 2, 3, 4. Another bond to the hydrogen that's not shown but implied. And the hybridization on this would be 1, 2, 3, sp2. So anyways, I would just go through, pick them apart, write it down, then try to find out, after you've written those down, try to figure out which one matches up with what you just determined. Sigma bonds and pi bonds. Have you studied sideways overlap versus direct overlap? Sigma bond is the single bond, or the first of a multiple bond. So, let's see. This is a sigma. One of these is a sigma. Sigma, 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 sigma. One of these is a sigma. One of these is a sigma, and sigma. What I count? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13-ish. I think it's going to be this one. But the pi bond are the second or third in the double or triple bond, and they form as a result of sideways overlapping of unused orbitals, in many cases p orbitals. So here's a pi bond and here's another pi bond. Here's a pi bond. Here's a pi bond and here's another pi bond. That's 1, 2, 3, 4, 5 pi bonds, and I counted 13 sigma bonds. You could say sigma starts with an S, and I think about single bonds, but yeah. Whoa. Professor Atwood, he goes crazy sometimes. Take a gander at this one. You might go through and pick apart the hybridizations on one: carbon, oxygen, nitrogen, carbon, sulfur, carbon, carbon, oxygen, nitrogen, and carbon, and see what you get based on the practice I've just done above. I was kind enough to draw the lone pairs in there, so don't forget about the lone pairs. Yeah, that's enough listening for now. Go practice a little bit and relax too.